So I'm Milan. I'm a climate scientist at MIT, as introduced just a few minutes ago. And today, what I really want to talk about are some of the data challenges that we face in earth sciences. Coming from climate data, my focus will obviously be more around weather and climate data, but most of the stuff will basically apply to anything that's some kind of gridded earth data. And as a motivation, I brought today this plot that is from ECENT-OBF's data archive site. So ECENT-OBF, that's the European Center for Medium Range Weather Forecast, probably the biggest data archive that we have in our field. So last year, they were just hitting the 600 petabyte barrier. They're getting very close to 1 exabyte now. And the question is really, in the coming decades, where would this data, the size of this data archive be? It's exponentially growing. So in 2040, it could well be hitting 1 zettabyte, by which it kind of would overtake Google's data archive from a couple of years ago, at least what we estimate its size is. And so you can really see on this graph of how important reasonable data compression is. So I've put in the figures here for a 10x or 100x compression, so making things 10 times or 100 times smaller. And so you can really see that this is an absolute game changer. Otherwise, we would easily end up with way too much data that we can basically ever analyze. And really trying to cut down on this data suddenly makes it much more manageable to store the data, but also to obviously facilitate the sharing, to send it around, to analyze it, and so on and so forth. One of the big problems, though, if we talk about data compression, especially in our field, is that we have such a variety of different types of data to look at. So these are just a few examples here. Left is brightness temperature as it's measured, for example, from a satellite, where you can see that if you have a really clear sky, there will be some really smooth data once the ocean is visible underneath, for example, but once there's clouds in between, it gets really, really patchy. If you look at things like other variables, you may even have absolute differences in their structure. For example, here nitrogen dioxide up in the stratosphere, where you can see like a pattern of the sun superimposed on some turbulence, but then nitrogen dioxide at the surface suddenly has a lot of point sources. You can even see ship tracks in it, and so on and so forth. So really finding a one-off solution for data compression here is a very, very, very tricky challenge. And so really as introduced already earlier, really the one thing that I want to talk about today is kind of this topic that I've been working on over the last few years, is the question that, because all our data sets basically just come in massive arrays of numbers, what do these numbers really contain? And which of these, well, essentially, because in the end they're zeros and ones, which of these bits do contain more information and which of them contain less information? So if you start here, just like looking at whatever array on the left, this is now presented obviously in decimal, or whether you present it in binary doesn't really make a difference, but you have somehow the most significant digits on the left, or bits on the left, and the less significant ones on the right. And so we definitely would agree that something like the sign is absolutely real, right? If I would just like swap the sign bit, we would immediately notice that something is off. But if I were to like swap one of the last bits in this data set, you probably wouldn't even notice that anything changed. And so the really question is there an objective way that we can separate out the real information that we have here on the left and the false information that starts at some point here on the right? And this really comes hand in hand with data compression, because the stuff on the left, as you can see, that there's a lot of similarity in the data, is very compressible, whereas on the right, everything is really noisy. So that's really incompressible. There's an entire information theory behind it that we've kind of worked through and formulated different metrics. And this is just the high level summary of that. So this concept that we came up with is called the bitwise real information content. And the idea is really that you start with some grid data, you look at it in its binary representation. So for example, floating point numbers, and then you look at every bit position in a floating point number individually. So for example, you look at basically the spatial distribution of all the sign bits, or the spatial distribution of all the fifth exponent bits, and so on and so forth. And the question then is, if you were to look at one of the bits, what does this bit tell you about the neighboring bits? And so we really formulated this as the mutual information between adjacent grid points. And the idea is very simple, that you say, well, if somehow the neighboring bits have something in common, if they're basically certainly adjacent to each other, then there's more mutual information. And if they basically just appear randomly, then there's less information. And so that way you can basically squeeze this information about coherence of your bits in your data set. You can squeeze that into a single number for every bit position. And so we did this for a large data set. You can see here a lot of different chemical atmospheric variables on the left. You may spot variables like methane or CO2 in it, but there's also a lot of aerosols in it. And now we've color coded. So the darker the color, the higher the information in a given bit. And so this is just using the single precision bit encoding. So you have a sign bit. This is kind of a data set where basically all of the variables are positive anyway. That's why the sign bit does not contain any information here. Then you have a lot of information in the exponent bits. And then actually in the mantissa bits, a lot of information very quickly drops out. And so what we learned from this is that while we usually store a lot of bits, like if you store floating point numbers, single position floating point numbers as it is, you will have 23 mantissa bits. Many of these mantissa bits actually do not contain any information. The next lesson we learned from this is that depending on the variable, depending on the field you look at, there will be different information. So some variables like CO2 require a much higher precision to store them at as some of the other variables. And so kind of like a one-off precision for all of them doesn't really work. If you then think about this as, well, if we kind of say, well, if there is some information towards the end of the bits that you could just cut off, it really lends itself immediately to a compression technique, right? Because once you store only the zeros and you remove them, the size of your files definitely gets much smaller. And here's an example where we've done this for water vapor. So on the very left of this field, it's basically the original data set as it is. And then towards the right, we've cut more and more of these mantissa bits off, and you can basically see then how the compression factor at the top starts to increase. So in the middle, we're around like 40 times smaller than it used to be. Whereas down the right, we really enter cartoon land. That's obviously we cut off much more information than we actually want to cut off. And so kind of like the sweet spot is somewhere in the middle. So really saying like, okay, well, if you start with a number, you replace the digits that you're not interested anymore because you've identified them as false information. You represent them with zeros, and the same holds for the bit encoding. Like it's kind of like the same perspective on there, where like you store your data in bits. Obviously, then you replace the bits with zeros. And so, in order to make this concept work in our favorite programming language, I've basically implemented the reference for this in this package called bitinformation.jl. But what I've found quite exciting is that there's actually also a lot of other people that have taken this up, mostly in Python-based data sets. And so basically, I hope that there kind of will be a community of people using this concept. In the end, basically all of these Python implementations just wrap around my Julia functions, because I find it's much easier to write many of these bitwise operations in Julia. And so just as the last slide here, I want to give you a little overview of how you can do this in practice. And there will be a hands-on session tomorrow where I will also be around, and I'm very happy to chat more about this. So the first step that you always want to do is you want to analyze your bit information content. So there's this package using bit information. Then let's say you take some kind of abstract array. I should have probably written this down here, but A is an abstract array here. You load it from a file, whatever you have. And really then the only function you have to call is bit information of that one. And that gives you a vector of as many bits as there are in your elements in your data set. So for example, for a single position, you will get a 32 element vector back. And every single number then just represents how much information between 0 and 1 there is in that bit. And so you can look at it, you can plot it as I've done here. So you see, for example, something like temperature has a different information than something like water vapor, and something that is completely random would have no information at all. And though in the end, it is actually surprisingly tricky to find the exact cutoff to automate that. But you can already see something like temperature, you may want to have like maybe 9 or 10 mantissa bits. But something like water vapor, you would probably need less. Once you know how many bits you want to keep, you can just apply this rounding function that is just binary bitwise rounding. And then you can see basically if you, for example, call the bit string function, you can see that there's a lot of zeros then towards the end, towards the lesser significant bits. And then really the last thing you have to do is just compress it. So depending obviously on what kind of data format you use, whether you use like netcdf or any kind of the other data format that are out there. Here, just an example using JLD2. So really just like if you then switch on the lossless compression that these formats provide, you'd basically just store that one and you will have a file that is much, much smaller than it originally was, while actually still containing all of the information that is necessary for your analysis. And this is where I would like to stop. And I think I'll hand over to Fabian Gans now, and I guess we'll take questions then towards the end. Thank you.
Yeah, thanks a lot, Milan. Maybe you can stop sharing your screen so that. Yes. Great. Okay, then as I said, thanks a lot, Milan, and I'll start now with the second part of the presentation, which is now less about compression, but about storing large data at all and analyzing large data. And I'll just begin with our study object at all. I mean, like, so the thing, I mean, when you talk about raster data, or I mean, like we are using it in climate science, you usually use these spatial temporal data, but there are also these data cubes of remote sensing data. You store them, you can often see them as multi-dimensional arrays. I mean, like, so this is what we usually store on disk. So it's basically, yeah, it maps very nice to a Julia array. It's a 3D array. And what your storage library usually does, I mean, like, no matter if you use, I don't know, a netcdf or HDF or whatever, is it lets you extract certain subparts of your data. I mean, like, so sometimes I want to read a single time series at a certain spot, or sometimes I want to extract like just one map from my data, or sometimes I need some rectangular hypercube. So but this is usually like the interface that is provided for me, and when you start dealing with these netcdf files or HDF files in the daily work, you get used to this. I mean, like, for you it's just data, but at least as long as the data is small. But if the data volumes grow and you have these kinds of data cubes now on very high resolution, I mean, like high spatial resolution and high temporal resolution, then you start running into problems with this kind of arbitrary data access very fast in the way that it can get very slow. So I mean, like, the problem is, okay, the data does not fit in. So imagine you have such a large data cube and it does not fit into your computer memory anymore. So you need to read the data on demand. And one of the main problems that when you look at this a cube, I mean, like, the way you want to store it is that your disk storage is not a 3D thing. Now we have an echo. Okay. Can you maybe mute again? I have an. Oh, okay. Good. Like the storage on your disk is not 3D, but it's linear. So that means usually usually you have to I mean, like, data which might be close. Sorry, there's one participant not muted, and I have this echo. Okay, I'll try again. Yeah, so that means data which is really close, maybe in time or in space, is not necessarily close on disk. So and another problem that you have when the data gets very large is that as soon as the data is compressed, it completely prevents random access of data which is on disk. So just imagine we give this whole data cube now into a compression library and compress it, and we just want to extract a single data point or a single time series from it. What you would have to do is that you would need to read the whole data set and uncompress it to do the random access into it. And to avoid, or to partially avoid these problems that that you get, is that you basically divide your big array, I mean like your big 3D data set, into smaller chunks. And this is possible with like all the netcdf and HDF libraries, but also with new file formats like ZAR, TiDB, HDF5 Cloud, or cloud optimized GeoTIFF. And because in these I mean, and these new formats popped up because like compression is really important, like in these cloud applications, and they also make it easier to store the data in buckets, I mean like than it is for netcdf. So basically there are different ways to chunk your array. I mean like so you can chunk it only in space, for example. I mean like then just imagine that you put these blocks into your compression libraries, and then each of these blocks of data, I mean like here it's 1 year always, forms a unit in itself. And the big rule when accessing this compressed and chunked data is that the time that you need to extract some data is not proportional to the amount of data that you extract, but it's proportional to the number of chunks that you access. So that means when from this data set with this chunking, if I want to read a full time series, then I have to still uncompress all the data set. I mean, like so because because I can't just because I have to look into every chunk basically. If I want to extract a single map, that can be quite fast. I only have to extract a single chunk. So what you usually want to do to allow efficient access into all directions is that you basically do some chunking in time and in space. I mean, this is at least what I prefer because I'm doing a lot of time series analysis as well. And so when you access now, for example, a single map, then you only have to read a subset of the chunks. I mean, it's still more data than you would need to read, but that's okay. And when you want to access a single time series, then you also need to read only a subset of the chunks. So, and this is really what this chunking is about. And what we now need, I mean, like this is now the data side, and what we really need is basically a library that can efficiently work with these chunked arrays. And since this is implemented in many different file formats, it would be good to not re-implement this for every file format, but to basically have one library that deals with it. And this is this diskarrays.jl package that already Raphael has mentioned on Monday. I don't know how much he talked about it in the hands-on. I couldn't attend this one, but it basically does two things. I mean, like it provides an abstract array implementation for arrays which have slow random access. Right? So yeah, I don't know if I should do this detour, but when you look at this abstract array interface, you see it's when you usually use it, then it's completely bound to efficient access to single elements. So all you usually define for an abstract array is how to read a single element for the array. And then the Julia base library will basically always, whenever you do more complicated indexing, it will just fall back to indexing into individual points. And as I explained, this is really not possible for these kinds of arrays, because if I do like here, if I want to read a full time series and I just start looping through the time steps and extract every single point, then I would have to, then I have a lot of additional reads and a lot of additional calls into the C library and a lot of uncompression. So this is just not practical. And so that's the first thing that it provides. I mean, like it basically captures all the gets index and show and so on, and makes sure that there's never a random access, never an access to single elements, but that always blocks of data are read. And the second thing that it does is that it provides primitives to handle these n-dimensional chunks. I mean, like, so to talk about the chunking structure of arrays. So these are basically the two main things that disk arrays.jl provides. And it is already implemented or as a backend for data access in ArchGDAL, in netcdf.jl, in SAR.jl, and in grip datasets.jl. So these they all depend on disk arrays. And just as a short demonstration, so when you use, for example, the ZAR package, which opens its multidimensional arrays as a disk array. I mean, they are abstract disk arrays. So here I open a data set directly from the cloud. So this is like now stored in Google Cloud Store in a Google Cloud Storage bucket. That's just some CMIP6 run. I open the data set, I get a variable, and the first thing that disk arrays is doing is that, I mean, although this is an array, it doesn't print me the typical Julia array because it doesn't want to do any data traffic. It just shows you the size of the array and the type of the array, but it doesn't print you an overview of the data. I mean, like, so basically this is what you have. And I, through the disk arrays package, I can ask, okay, I can ask the array, okay, what are your chunks? I mean, like, this is this each chunk function, and then it gives me back an array that's tells me, okay, I have this chunking structure. So this array is not chunked in longitudes, not chunked in the latitude dimension, but only in the last one, only in a time. And there we have 116 chunks. And you see the indices of each of these chunks. So this is very useful because you can use this to do like batch processing of your data, and you know that you will always access your data set in a chunk efficient manner. And in the detail, it gets a bit complicated. So for example, when you create views, I mean, like here, let's do something. Let's just take every second longitude and every third time step and until the time step 5000. And I still can look at the chunks, and you see that then the chunk sizes are adapted, but they still align with the original chunks of the data. And although I have now irregular chunks because I have these 3 steps and so on, I mean, like, all this is possible, and there's a lot of nitty-gritty detail work, especially with views and with strange views that we implemented in this disk arrays package, or that you extract like a number of time series like at certain points or so. I mean, like, that you give a long vector of longitudes and latitudes, and you just access the array at some longitudes and latitudes. I mean, like, this is you can still read from the data, but it's programmed in a way that it always makes sure that when you do some get index operation, that every chunk is accessed only once. So that this is still quite fast on your machine. Okay, and a typical workflow when you want to do some data analysis would be, as I mentioned, I mean, like, so you have your array, and then you just do for index in each chunk of PLS of my disk array, and then you basically get these indices always as ranges, as boxes, and you know, okay, in the next step you should do something with this chunk, and then you know that your access is always chunk aligned. And yeah, we also implemented basic reductions, like, for example, simple reductions over a dimension. So I can do, this is now again on the remote array, I mean, like, which needs like some internet connection to Google Cloud or so, and then I can do a mean over these steps over the third dimension, and it will read the necessary chunks and do the computation in a much more efficient way than if you would use the normal abstract array fallback. And also broadcasts are implemented, lazy broadcasts, as was already shown by Raphael on the first day. So, but then what should we do when we want to go a bit beyond broadcasting and reduction? And so what about typical like map slices operations, or when you want to do multivariate operations? So for example, you have like some disk array here, one array here and another one here, and I want to operate on them together. I want to do operations in parallel. I mean, like, that's the main point of moving data to the cloud and have chunked things so that different workers can work on different parts of the data. And here we made this package, this yaxarrays .jl package, which is an attempt to solve some of these issues. And so it's first of all, when you look at it, the yaxarrays library, it's yet another library for arrays with dimension tables and values. I mean, there's already a zoo of them. But the special thing about this one is that behind the scenes, a Yax array is defaulting to out-of-core computation and to out-of-core storage from the start. That means this has in some ways the effect that it sometimes feels a bit more awkward to use, and it's much less documented than Rusters.jl. So when you're a beginner working with data, and especially when you have a bit smaller data, I would also really suggest you, okay, use Rusters.jl, but there is a lot of work invested in these large-scale processing problems and large-scale processing tools. And just to show a very short example, you can open this you load the yaxarrays package, you open a tar data set, and then you see, okay, I have longitude, latitude, and time dimensions, and I have a lot of variables. I have some variables in there like air temperature, land surface temperature, GPP, like gross primary productivity, and so on, some land surface things. And I can also merge the different variables into a new axis. I mean, like now I get a 4-dimensional array, for example, when I just call cube here, so that I have longitude, latitude, time, and variable as another dimension. And you see the total size of this array is now 33 gigabytes. This is all happening on my laptop. I mean, like, so the storage size is smaller. I mean, like, this is basically the uncompressed size that it's showing here. And yeah, I can, as I said, I mean, like, so one thing that we implement is a map slices. So for example, I can define my function, apply median, and then I just check for nonce and compute the median of the data. And then I can just say, okay, map slices, this apply median function, I apply it on my data cube across the time dimension, and I give it like some maximum cache size, and yeah, then it's just computing it. And so here on these 33 gigabytes on my laptop, it takes 62 seconds. Okay, it says there was 69% recompilation. So yeah, I mean, like, it's actually quite fast, and it can't load all the data in memory at once. Yeah, so yeah, that's the result when you plot it. So you get then a map of the median, and basically now median has been applied to every time series because I specify the stims equals time here. And it's doing this computation. And so this all sounds quite natural and simple, but there's actually a lot going on in the background when you call this map slices over the dimension here. I mean, so the first thing to know is really that this Yax arrays is working together with disk arrays, and it's aware of the chunking of the underlying data. So it really looks deeper into your data set, and then it says, okay, I need to loop through for this data. So it looks where to get full time series from. So what it will probably do is, okay, it decides on this first chunk, okay, I need to read these blocks of data to get full time series. So it will read this whole block that I highlighted here into memory. And then it will start, okay, to take the first full time series, and it will basically run this inner loop now through the single pixels and process the time series and compute medians on them. And then when it has arrived at the end, it will read the second set of chunks, will start again its inner loop to process these time series, and so on. And it will do this, like, there's some optimization in the background to use quite large processing windows, but to do this always aligned with the chunking, with the chunks of the underlying data. And of course, this is very trivial to parallelize. So whenever you load some workers, you use the distributed JL package and you add some workers. it will automatically distribute the loading task of data across different workers. So basically then when you have two workers, they will both now load their piece of data and then start processing these beams of times. And also when you have multiple threads on each worker, it will do this computation also on the multiple threads. So you don't need to care about this. I mean, just with the single map slices line of code, all this will be happening in the background. So there are also much more complex workflows possible. Of course, then the interface gets a bit more complicated, but you will see that in the hands-on tomorrow. And but just to summarize, the general philosophy of this JAX-Arrays JL is that the user comes with some function they want to map over a big data cube that is chunked, and then you basically give it to JAX-Arrays, you tell it what to do with that function, and then JAX-Arrays maps it over the data on disk and writes the output. And yeah, so okay, I'm running a bit short of time. I just saw just the things that it does not yet provide the JAX-Arrays JL package. It's not doing lazy function application yet when you do this map slices. So basically, it's always executed at once, the operation, and there is no coupling yet to the rasters.jl and dimensional data.jl universe. Although there are some conversion functions, I mean, like, because we know that many people like to use these packages, and we also like them because it has very intuitive subsettings and so on, subsets and so on. And one of the next steps will really also be to work towards this, that you basically don't have that we will try to put what we have in the out of core processing on top of the rasters.jl, but that's a little bit difficult, yeah, because things get intertwined and so on. So, but that's something we want to do in the future. And we also provide a table interface. I mean, like, so Raphael has already described the concept of how you can make a dimensional array or like a geo array to a table. I mean, we also provide this, but as I mentioned in the beginning, everything by default is out of core. So you can create such a table here. Now it's I use this cube table and I just put it in. I say, okay, GPP is this data cube and air temperature is this data cube. And it just tells me, okay, you get some data cube iterator with 40 subtables. Yeah. And the point about this is that that it already says, okay, I don't load any data, but I give you an iterator over tables, and I can just take now, for example, the 33rd subtable, I mean, just some random table, and convert it to a data frame, and then you will get a subset of the data which fits into your memory. I mean, so this also has an argument where you can set, okay, how much memory do you want to allocate to each of these subtables? So, and this is really a structure that you can nicely use for out of core aggregations of data whenever you need them. I mean, so you can, that we will have an example tomorrow in the hands-on where you can also do like a country mean of certain variables, but then with parallel processing, like in a using the distributed .jl package. I mean, so that you can really distribute your computations also that happen on this kind of table level. And so that's a short overview, and I hope Felix will explain this in a much better detail tomorrow in the hands-on session that he's going to give on this JAX-Arrays JL package. And I just want to say a few words about the future, like the future plans that we have. I mean, as I already mentioned, I mean, like, rasters.jl is doing many basic things, especially also the coupling to the whole geo interface world and rasterization, and but also the simple opening of data is doing many things better than JAX-Arrays is doing, like in the basic array handling. And I also have the feeling that it's for myself and our group impossible to maintain such a large set of functionality. I mean, like, so much on the processing side and on the data access side. So we will try to concentrate on this out of core processing part in the future. And I have recently started a new package called disk array engine.jl, which is really supposed to provide all this out of core processing, but on the disk array level. I mean, like not on YAX arrays, but on the disk array level, so that it will be much easier to implement this functionality than also on top of a rasters.jl array. So that's basically what we want to do in the future to make this more accessible, all this machinery. Until then, you are still very invited, I mean, to try YAX arrays, to try the package. Yeah, be aware that that's like most of the development, or at least my development of new functionalities, will happen in this disk array engine, which is not yet ready to use. I mean, but I started and putting in functionality and so on. And yeah, so and yeah, also this disk array engine, I mean, like, it will provide like interfaces to do some operations on large array, but it's probably not meant for direct user interaction, but just to be called by other packages like rasters.jl to do some computations in the background. So if you want to, you can keep track of what is happening there if you're interested.